Cardiovascular physiology. What happens to the cardiovascular system when we exercise? Here's a little video that reviews the material we covered in Chapter 4. You can find this at YouTube, science.tv. I'm going to talk over it right now because we don't have time to watch the whole thing. Exercise places stress on the body. Your muscles are working harder than normal, and as a result, they require more energy. In order to create ATP, or energy, the body requires more oxygen. In order to supply the additional oxygen, the cardiovascular system must work harder. Let's examine all the variables introduced in Chapter 4 to understand how they change with both acute and chronic exercise. Acute exercise refers to exercise that's happening right now. If you stand up from your desk and start running, you are performing acute exercise. Chronic exercise is activity performed over a long period of time, perhaps 6 months or several years. The result of chronic exercise can be referred to as a training effect. Let's start with the central cardiovascular variables. How does the heart deal with the higher metabolic demand of exercise? As we know, heart rate is the number of times your heart beats per minute. The heart rate increases linearly to max during progressively intense exercise. If the exercise intensity remains constant, the heart rate will level off. This is known as steady state exercise because the increased demands can adequately be met by the cardiovascular system. Training heart rate is an effective measure of acute exercise intensity due to the fact that the linear increase in heart rate is directly correlated to the linear increase in VO2. What would you expect the training effect to be on heart rate? Well, the chronic effect of exercise training is that the resting heart rate becomes lower. Also, fit people are able to perform more work at a lower relative intensity. For example, if 2 people are running a mile at a 10-minute pace, the fit person will feel less intensity and have a lower relative heart rate than the unfit person. There can be no training effect on the maximum heart rate. It will actually decrease with age in both fit and unfit people. Moving on to stroke volume. Hopefully we remember that stroke volume is the amount of blood ejected per beat. So this is the amount of blood that's in the heart when it's relaxed. This is the blood that is in the heart when the heart's actually pumping or squeezing. The amount of blood ejected per beat increases curvilinearly until the exerciser reaches 50 or 60% of his or her maximum heart rate. Stroke volume increases because the left ventricle fills more completely, stretches further, and recoils elastically more forcefully to produce a greater contraction. Endurance training often results in a lowering of the resting heart rate and an increase in resting stroke volume. This means that at rest, a fit heart works more efficiently to deliver oxygen to the tissues. It also enables trained athletes to produce larger proportional increases in cardiac output, meaning that they can perform more work. Moving on to cardiac output, which we may recall is the product of heart rate and stroke volume. Cardiac output can increase from 5 liters up to 20 or more liters per minute with exercise. When cardiac output increases with exercise, most of the change can be attributed to an increase in the heart rate. Remember that stroke volume peaks at 50 or 60% of max heart rate, so its contribution after that point is minimal. The blood vessels also have to change to accommodate exercise. The total peripheral resistance is the sum of all forces that oppose blood flow in systemic circulation, such as blood viscosity, or how thick it is, vessel length, and vessel diameter, how wide it is. Vessel diameter is clearly the most important. Because of their small radii, the arterioles provide the greatest resistance to blood flow in the arterial system. As exercise intensity increases and vasodilation occurs in the muscles, the total peripheral resistance in those areas decreases. During exercise, certain organs need more blood flow than others. For example, the skeletal muscles require more blood flow, whereas the digestive tract requires less. At the same time, the skeletal muscle arterioles dilate. The arterioles to certain other areas help compensate by constricting. The brain requires the same amount of energy, whether at rest or exercising, although the percentage of blood flow directed to the brain changes significantly. Obviously, there are changes in blood pressure with acute and chronic exercise. The systolic blood pressure increases linearly. You may recall that blood pressure is the force that drives blood through the circulatory system. During maximal exercise, systolic blood pressure may reach 180 or 200 millimeters of mercury. This is due to the sympathetic stimulation and increased stroke volume. Diastolic blood pressure has the lowest resistance to blood flow, as it stays the same or decreases slightly. It is important for the diastolic blood pressure to remain low so that the ventricles can fill with blood. Muscular system or peripheral variables. AVO2 difference or oxygen extraction. This reflects the muscle's ability to utilize oxygen. Oxygen extraction is the difference between blood leaving the heart and mixed venous blood returning to the heart after it has passed through the muscles and given up some of the oxygen. Conditioning results in an increase in the AVO2 difference, indicating greater oxygen utilization by the working muscles. Exercising muscles can reduce the oxygen content of venous blood from 1/2 to 1/3 of resting levels. This indicates that your muscles are extracting a higher proportion of the energy delivered to them in the arterial blood. As much as 85% of the oxygen in arterial blood can be removed during maximal exercise in highly trained individuals. With long-term exercise, your body can create a higher density of capillaries and also increases the production of NO for promoting vasodilation. Mitochondrial density also increases. The body adds more mitochondria to the muscle cells to enable them to create ATP more effectively. Remember, mitochondria are the powerhouses of the cell where aerobic metabolism takes place. VO2 max, or maximal oxygen consumption. This is the ability of your body to take in, transport, and utilize oxygen during maximal effort. The ability of your body to take in, transport, and utilize oxygen during maximal effort. VO2 increases linearly with increased exercise intensity until maximal exertion is reached. You may recall this equation. VO2 max equals cardiac output multiplied by oxygen extraction. A point occurs beyond which oxygen intake can't increase, even though more work is being performed. At this point, you have reached VO2 max. Considered by many experts to be the best indicator of cardiovascular fitness, VO2 max involves three systems: pulmonary, cardiovascular, and muscular. With acute exercise, VO2 increases linearly with intensity until maximal effort. With chronic training, VO2 max increases as the cardiovascular system adapts to the regular stress. We've discussed many of these adaptations, such as increased stroke volume, increased cardiac output, and increased AVO2 difference, that add together to allow VO2 max to increase so significantly. Some people are able to improve their VO2 max by 50%, although the average is closer to 20%. There are some genetic limitations to any type of training, as well as individuality in the response to training. The highest VO2 max readings are in the high 90s and belong to cross-country skiers and cyclists. The highest VO2 max readings recorded for women athletes are in the high 70s. Let's take a look at this summary chart of what happens to cardiovascular variables with acute exercise. It's helpful to review and check for understanding. When exercise commences, heart rate, stroke volume, and cardiac output all increase due to sympathetic stimulation and increased venous return. Systolic blood pressure increases to deliver more oxygen to the body, whereas diastolic blood pressure remains constant in order to allow adequate rest and filling time. Total peripheral resistance decreases due to vasodilation in working muscles. Oxygen extraction increases in the muscles so that ATP can be produced. Because both cardiac output and AVO2 difference increase, VO2 increases to meet the additional metabolic demands of the body. The respiratory system. Once again, this video can be found on YouTube on science.tv. The respiratory system is overbuilt for the purposes of providing gas exchange during exercise. We never really reach maximum capacity for ventilation during exercise. Lung volumes are largely a function of age, height, and gender, as opposed to fitness level. The lungs are not a muscle that can be strengthened through training. It's unlikely that pulmonary function limits ability to exercise unless a disease such as asthma, bronchitis, or emphysema impairs lung function. As your exercise intensity increases, your body must provide more oxygen to your working muscles. You may feel out of breath as your breathing gets progressively faster and deeper. It may feel like being out of breath requires you to stop exercise. However, the relative weak links that limit exercise performance are oxygen transport and utilization to skeletal muscle, not the respiratory system. Acute changes are that the respiration rate increases, perhaps to 40 to 60 breaths per minute. There's minimal change with chronic exercise. Tidal volume increases with acute exercise. There are minimal changes with chronic. While at rest, expiration is passive. When exercising, active expiration, exceeding 30 to 40 breaths per minute, require the muscle involvement of the internal intercostals and abdominals in order to breathe more deeply. At normal altitudes, our ventilation is more sensitive to the need to expel carbon dioxide than it is to the consumption of oxygen. Minute ventilation